Normally, you're just given this mass percentage, and so I just wanted to calculate it there. But let's take a look at number 78 from the book. Number 78 is given. We're looking at this. How would you name this? This one we could either name using molecular or ionic, because this is a semi-metal. And so this is its most common name, silicon carbide. This is its ionic because C4 minus is carbide. This would be the silicon ion, cation, which would be a silicon 4. And so silicon carbide, or you could say silicon monocarbide, but silicon monocarbide is awkward. This is silicon carbide. We can tell the ratio based on the charge in the carbide ion. But silicon carbide is made from sand and coke. So sand is this. How would you name this? Sand. Well, this one is named, silicon dioxide, and it's just because it's traditional. So this one's named like the ionic compounds. What coke am I talking about? So this is named as a molecular. And so sometimes the rules aren't consistent, but it's a semi-metal, so it's between molecular and...
So silicon's made from coke?
Silicon carbide's made from coke. You know what coke is?
Cocaine?
No. Coke is do you know coal? Coal?
Yeah.
What is the composition of coal?
Carbon?
Carbon. Is it pure 100% carbon? Depends on what type of coal you have. Coal's a mixture, and oftentimes, and you have like anthracitic coal and a bunch of other coals. Well, this particular coke is a mixture that contains some.
Oh, coke?
Coke is C-O-K-E.
Oh, coke.
Coke, this particular coke contains 88.9% carbon. So the way silicon carbide's made is they take the sand, silicon dioxide, and mix it with coke. The coke is going to supply carbon. And then what we want to do is we want to form silicon carbide. What do you think the other product is? O2 might be a good one. It could be. CO2 might be a good one. But under the conditions of this,
Carbon monoxide.
carbon monoxide is correct. Yeah. CO. And so this is the commercial reaction here.
It's going to be two
CO and 2CO.
Yeah, so we need to balance this first. So we need 2 C's and 2 COs. Okay. And so this is just sand mixed with coke. The sand, of course, is not pure SiO2, but we're not going to worry about that. The coke is only 88.9%. So this is our stoichiometry map. It's going to be, we're going to start off with the percent carbon here in mixture. Actually, this one, we're not going to start. We're going to start with this. We're going to start with tons of mixture. And then we're going to know the percent carbon in that mixture, and then we'll go to tons of carbon. And then from tons of carbon, we could go to et cetera, and rejoin our stoichiometry map. And so let me read off the problem. The problem says that how many kilograms of carborundum, what is carborundum? silicon carbide. Silicon carbide is also called carborundum. Carborundum.
Well, what do they call it that?
I don't know. Carborundum.
That makes no sense.
How many kilograms of carborundum can be prepared from 727 kilograms of coke? So we're going to start off with 727 tons of coke. And then what we want to do is we want to figure out how many kilograms of silicon carbide we're going to get.
How many tons?
Yeah, how many tons of silicon carbide we're going to get. And so what we have here is we have moles of A to moles of B. Now A is going to be silicon, actually not silicon, carbon, and B is going to be silicon carbide. And then what we're going to do is we're going to go, I think, grams of A here, and then from the grams of A, we can start off with grams of A mixture. But we have to do a few additional steps because we don't have grams of A mixture, we have tons. And so there are multiple paths we can do. We can just go ahead and do this, or we can do it this way. I'm going to do it this way because this is the way I normally do it. I always do it the same way each time. Okay, so we aren't starting with grams of A mixture. We're starting off with tons of A mixture. And so what I'm going to have to do is I'm probably going to have to do multiple steps here to get to grams of A mixture. And then from grams of A mixture, I'll go to grams of A if I know the percent by mass composition. In this case, I don't have to calculate it myself because it's just given 88.9%. The mixture is varied as far as the composition goes. So we'll start off with 727 tons of coke. And then we need to go and get rid of tons. Now the problem is that metric tons?
Like 2,000
Or,
to 1 ton.
yeah, or is that normal tons? And so do they tell us?
So it's a.
Oh, wait. We don't have to worry about it. Because I misread the problem. This is not tons. This is kilograms. That makes it a lot easier. Yeah, sorry about that, but it makes it a lot easier.
That'd be a lot harder.
So tons would be a lot harder because we don't know. They didn't specify metric in my head. They didn't specify metric or imperial. But we'll do 727 kilograms. Now this is easy. We'll go from kilograms to grams. Okay, now we have grams of mixture. And then what we can do is we can get grams of pure A. And so I have this. 88.9% by mass carbon means I have 88.9 grams of pure carbon for every 100 grams of mixture, which is called coke in this case. And so I'm going to have 88.9 grams of pure carbon per 100 grams of coke. Okay, and so this tells me, you know, if I had 100 grams of coke, I'd have 88.9 grams of pure carbon. Okay, then what do we want to do? We go from grams to moles. And I have this one memorized. 12.01 grams of carbon is a mole of carbon. It's from the periodic table. And then where do I want to go? Moles of silicon carbide? Yeah. 1 mole of silicon carbide requires how many moles of pure carbon?
1. Oh, 2.
2 moles of pure carbon. And then I want to go from moles of silicon carbide to grams. But I don't have silicon memorized, so I have to look that up on the periodic table. 28.09. I'm going to round it, even though I tell you to avoid rounding error. I do this for the molar masses for speed. 2809. Carbon I have memorized, that's 1201. And so altogether I'm going to get 10 here. 40.10. And so 40.10 grams of silicon carbide per mole of silicon carbide. And then I'll go to kilograms. And so every kilogram has 1,000 grams. And then just make sure the units cancel. This is critical in dimensional analysis. You have to make sure the units cancel. So kilograms cancel. Grams of coke cancel. Grams of carbon cancel. Moles of carbon cancel. Moles of silicon carbide cancel. Grams cancel grams, and that leaves us with kilograms of silicon carbide. And that's what we want. Kilograms of silicon carbide or carborundum. And let's go ahead and do the calculation here. That's going to be 7. Oh, what did you get?
0.00148.
0.00. Well, that's awfully small.
Never mind, I forgot to close it.
I got one.
The 1,000 cancel too, so that'll mean less punching here. So I'm going to do, I got 727 times 88.9 divided by 100 divided by 12.01 divided by 2 times 40.1 equals,
1,078.
I got 1078.9. Let's look at the sig figs. How many sig figs are we allowed?
3.
3. 3. And so doing this to 3 sig figs, we could say either 1,080 kilograms or 1.08 times 10 to the third kilograms or 1.08 megagrams. We don't use megagrams that much. Huh? Is that what you guys got?
The equation isn't even balanced.
Oh, the equation's not balanced?
There's 2 carbon on the left and 3 carbon on the right.
Oh, you're right, it's not balanced. That's not balanced, it's gonna screw everything up. And so we've gotta figure it out. Let's see, we have 2 oxygens. So how can we get 3 carbons on this side?
You changed it to 2
Not
to a
3
3.
on there?
Yeah, we changed the 2 to a 3. Okay, now is it balanced?
Yeah.
Okay. So that means I need to change this from a 2 to a 3, which means I need to change this answer. So let me recalculate the answer. So it's going to be 727. I could just do it myself. But 727, rather than punch the whole thing in again. 88.9 times divided by 100 divided by 12.01 divided by 3 times 40.1. 719.3. So corrected answer here should be 719.3 kilograms of silicon carbide, which is going to round to 719 kilograms of silicon carbide. Is that what other people got? Yeah, okay. All right, what I'm going to do is I'm going to stop here